Okay, so this is our simulation video for our analog project for fall 2024. I'm Zachary Ault. My two teammates, Nathan Dark and Benjamin Boals, worked on this audio equalizer circuit where generally we've got a audio signal that comes in and it goes through a preamp and then a filtering stage where we have a high pass, low pass, and band pass, and then they all get added up together and sent on to a power circuit to drive a speaker. Beginning with our preamp stage, this is a necessary part of our circuit because the audio signals that get put in either by a microphone or in our case, we use the headphone jack and music playing through an MP3 player. The signal is too weak to go into the filtering stage. And so we designed our preamp to be a gain of about 7. So that way we'd have a powerful enough signal so we could send it into each one of our stages. And so right here can be summed up as our filtering stage. And I'll start right here at the top. So this very top one is our high pass. It was based off of a second order Butterworth filter. It's characterized by the two capacitors in this configuration along with the two resistors. Due to our design constraints on our capacitor values, we had to choose ones to use in the circuit. We chose 4.7 nanofarad capacitors, and then we had a cutoff frequency of 2000 for the high pass. And so with that, we were able to use our cutoff frequency equation, so FC over 2 pi RC, and then we could solve for our values of R. And you can see that these two values of R are not the same. That's because each one of them is based off of this R value. So our top resistor is our R value times 0.707, while our bottom resistor is that R value multiplied by 1.414. And then once the signal goes through this filtering stage, it will then be passed on for later analysis.
And then for the bandpass filter, it starts with an inverter because when you have the two filters cascaded together, it puts them 180 degrees out of phase of the high pass filter and the low pass filter. So the inverter at the beginning helps bring the signal back in phase so we don't get any phase cancellation issues. And then the two filters, the high pass and the low pass, they were both designed the same way as the other two high pass and low pass filters, cascade together, but they also the cutoff frequencies are the opposite. The low pass has a cutoff frequency of 2000. Well, it's actually more around 2500. The low pass has a cutoff frequency around 86. And the reason we did those values a little bit differently is because we found that when working with the simulation, because of the overlap between the two other filters, the band pass or the high pass and the low pass, because of the overlap between those and the band pass filter, you get a big boost in the frequency response near the cutoff frequencies. So you get a less flat frequency response when, all the filters are letting everything through. So in order to compensate for that, we tried to widen out those cutoff frequencies a little bit to get a flatter response, and we still get a pretty good desired result of being able to control the frequencies we wanted. And then like the high pass, the signal goes out to a potentiometer that lets us control the magnitude of how much signal goes into the summing amplifier.
So then after the bandpass below it, you have the low pass filter, which is designed the same way as the high pass, but you'll notice it's just reversed and it uses the same equation as the first one. And it blocks out any current above 500. And all the filters then lead into the potentiometers, which control how much voltage is then pushed into the adder circuit, and it just does that by changing the resistance. So then they go into the adder circuit on the very right, and it just simply has a gain of 1. It just combines them. And then where the voltage source is located is where in our design our speaker would be. We just couldn't put it in the simulation. So the adder circuit simply just adds them together to then be drive into that speaker.
Okay. And then we generated four Bodie plots. One of them, each one of these constant blocks is has a value of either 0 or 1 in the plots. 0 allows all the signal to go through, and then 1 completely negates the signal. And so each one of those is put into this PowerPoint slide. And then Jackson will explain each one
Yeah,
of
so
them.
on this plot, this is all the potentiometers letting the full magnitude of the signal through. So this is our overall frequency response when none of the signals are attenuated. You can see that we have a slight wiggle in the response. We've got those bumps that are around our cutoff frequencies, and that's because of the overlap, because of the filters not being completely ideal with a sharp cutoff, since they have a slight slope to them where the bandpass and the other ones overlap. You get a bit of a boosting of the signals there. And then we can move on to the next one. So this is with the high pass filter, the potentiometer set to attenuate all of the signal coming out of the high pass filter. And we can see on this that we have a cutoff frequency around 1.2 kilohertz, which is a good bit lower than we were trying to design for, but um, so obviously some improvements in our circuit could be made there, but this was kind of the best result we were able to achieve at the time. Then you can move on to the next one. So this is with the bandpass filter set to attenuate the signal, and you can see that the cutoff frequencies there are around 500 and 2000 hertz, and that's pretty much what we were trying to achieve with that. Pretty close. We're very close. And then this is with the low pass filter set to attenuate the signal coming out of it, and you can see the cutoff frequency is around 500 hertz, which is what we were designing for. So obviously, the frequency response isn't absolutely perfect. Like in this one, you have a weird bump there, so there's obviously some further room for improvement in our circuit, in our design. But I think we came pretty close to achieving our goal within, the scope of what we learned in our class. And that's pretty much it. That's our simulation, the results from our simulation. Anybody else have any comments to add?
I think I'm good. But thank you.
All right.